Hello. Today we're going to talk about interpreting quantum numbers. Before we talk about how to interpret quantum numbers, let's remember what they tell us. Quantum numbers give us a location of an electron in an atom relative to the nucleus. Much like our home address tells people where within a specific area we reside. The quantum numbers provide a description of the volume relative to the nucleus where you are most likely to find a particular electron. Or, stated a different way, each quantum number describes an allowed energy state of the electron. Remember, these are the highest probability volumes where an electron will be found, because we cannot know both the speed and position of an electron at every moment in time. So we must trust statistics to provide us the highest probability volume in which an electron is located. One other thing to keep in mind as we discuss the quantum numbers that follow, and that idea is the idea of a Pauli exclusion principle. This principle states that no two electrons can have the same set of four quantum numbers. Every electron surrounding an atom's nucleus has its own set. Each orbital surrounding the nucleus holds a maximum of 2 electrons. In order for those electrons to have a unique set of quantum numbers, they must have opposite spins. You'll see why that's important by the end of this video. You may recall from your reading that there are 4 major types of quantum numbers: N, L, M sub L, and M sub S. Let's look at each in turn. N is the principal quantum number, which indicates the energy level the electron occupies. Values of N are whole number integers, beginning at 1 and increasing to infinity. However, in chemistry, we only typically see values ranging from 1 to 7. These are known as the energy levels or shells of a particular electron. L is the angular momentum quantum number, which indicates the orbital shape or sublevel where you can find a particular electron. L has values that range from 0 to n-1. This, as I already have stated, is known as the subshell and gives away the shape of a particular orbital. L and N, as you start to look at them, could have very similar numeric values, both positive, both whole number integers, one including 0, one not. As you might imagine, it's easy to confuse them. To help alleviate the confusion, the various common values of L have been assigned a particular sublevel or orbital shape. For L equals 0, that particular shape is known as an S. For L equals 1, the shape is known as P. And for L equals 2, the shape is known as D. And finally, for L equals 3, the shape is known as F. A little later on in your studies, you will learn what these various shapes actually look like. The third type of quantum number is M sub L, which is the magnetic quantum number, which indicates the number of orbitals and the orientation of those orbitals within a particular sublevel. For every value of L, there is an independent set of M sub L values. The values of M sub L range from minus L to plus L. These particular values explain why, for example, there is one type of s orbital. If it is an s orbital, L equals 0, M sub L can only equal 0, hence one s orbital. L equals 1, which corresponds to a p sublevel or orbital, then M sub L can be -1, 0, or +1. Hence, 3 types of p orbitals. In a similar fashion, if L is 2, the d sublevel, then there are 5 different d orbitals ranging with M sub L values from -2 through 0 to +2. And finally, if L equals 3, the F sublevel, there are 7 different F orbitals ranging again from -3 through 0 to +3. The Pauli exclusion principle, as I previously stated, indicates that an orbital holds a maximum of 2 electrons, and that those 2 electrons must be of opposite spin. The spin quantum number, m sub s, tells us the spin of each of the electrons. We label those spins with values of +1/2 and -1/2. The reasons the values cannot be plus and -1/2 is beyond the scope of this course's discussion. However, +1/2 means positive spin, -1/2 meaning a negative spin. In an orbital, the two electrons will have the same set of n, l, and m sub l values, as you'll see shortly, but they will each have a different value of m sub s, thus giving them a unique set of 4 quantum numbers as specified by the Pauli exclusion principle. Now, this all perhaps sounds a bit jumbled in theory. Let's try to look at some different pictorial representations to clarify what we have just said. On the screen in front of you, you see, in a pictorial format, the representation of all of the possible orbitals present in the n equals 1, n equals 2, and n equals 3 sublevels. Let's tackle these one at a time. Looking at the left portion of your screen under n equals 1. This is the orbitals present in the first shell or energy level. If n equals 1, the singular possible value for L is 0. If L is 0, we are talking about an S sublevel. Specifically, in this case, the 1s sublevel. In the 1s sublevel, here, there is one possible orbital, because if L is 0, m sub L can only be 0, and therefore we have one s orbital in the 1s sublevel. Let's move over here now to n equals 2. If n equals 2, L can be 0 or 1. Let's focus on L equals 1, as we have already looked at what happens if L equals 0. The only difference now is we have a 2s sublevel with one orbital. So let's focus our attention over here on L equals 1. If L equals 1, we are talking about a p sublevel, specifically the 2p sublevel. Within the 2p sublevel, if L is 1, m sub L can be -1, 0, or 1, meaning that there are 3 possible p orbitals in the 2p sublevel. If n equals 3, now L can be 0, meaning there's one 3s orbital. L can be 1, meaning there are 3p orbitals. Or L can be 2, meaning there are 5 3d orbitals in the 3d sublevel. L equals 2 gives us a d sublevel, and the possible values of m sub L are -2, -1, 0, 1, and 2. To summarize some of the things that I've just shown you, the number of sublevels in an energy level is given by the value of n. Look at the diagram. If n equals 1, there's one sublevel, the S. If n equals 2, there are two sublevels, S and P. If n equals 3, there are three sublevels, S, P, D, etc. The number of orbitals in a sublevel is given by the equation 2L plus 1. So let's pick on the 2P sublevel. In the 2P sublevel, L is 1. 2 times 1 is 2, plus 1 is 3. There are 3 orbitals in the 2P sublevel. If you want another example, let's look at the 3D sublevel. In that level, L equals 2. 2 times 2 is 4. 4 plus 1 is 5. There are 5 orbitals in the 2D sublevel. The number of orbitals in a particular energy level, let's say n equals 2, is given by the value n squared. 2 squared is 4. There is 1 2s orbital and 3 2p orbitals. In a similar fashion, if we look at the n equals 3 sublevel, 3 squared is 9. 3s orbital, 3 3p orbitals for 4, and 5 3d orbitals. 5 plus 3 plus 1 gives us 9 orbitals in the n equals 3 energy level. Pardon me. Since each orbital has a maximum of 2 electrons, the maximum number of electrons in an energy level is given by the formula 2n squared, where n is the principal quantum number. Let's pick on n equals 3. 3 squared is 9. 9 times 2 is 18. We've already verified that there are 9 orbitals in the n equals 3 level, and 9 times 2 is in fact 18 electrons. You can use these facts to predict the number of electrons, sublevels, and orbitals for any value of n, L, or m sub L. If you're still not convinced, let's try to look at another representation. Here's a simulation where we can select the particular value of n and then see all possible quantum numbers thereafter. Let's start simple with n equals 1. Let's now look at all possible values for L if n equals 1. As we've already seen, that is only L equals 0. And if we then want to see all possible values for m sub L, with an L equals 0, we can click again, and we notice m sub L can only be 0. Again, we know that this means in the first energy level, there is only one sublevel and only one orbital. Let's start over. Let's look at n equals 2. Now the possible values for L are 0 and 1. We already know what n equals 0, L equals 0 looks like. So what happens to m sub L if L is 1? To show all possible values for m sub L, for L equals 1, we click, and again, -1, 0, and +1. In other words, there are 3 different p-type orbitals. In a similar fashion, if we start over, we can look at n equals 3, which we'll skip for now. Let's look at n equals 4. The possible values for L if n equals 4 are 0, 1, 2, and 3. Assuming we already know what 0, 1, 2 look like, let's look at what m sub L could be if L is 3. In that case, the possible values for m sub L are -3, -2, -1, 0, 1, 2, or 3. Recall that if L is 3, we are talking about an f orbital, and that there are 7 f orbitals represented by the 7 values of m sub L shown here. Hopefully, these 2 simulations have helped you better understand what we mean by the quantum numbers. Let's see what we've learned. We're going to try and predict the quantum numbers. Which of the following sets of quantum numbers is not allowed? Take a moment and ponder this idea. Which one of these 4 sets, based on the rules we just gave you, are not allowed? Pause the video, think for a moment, and then hit play to hear an explanation of the correct answer. The correct answer here is the set of quantum numbers with an n value of 2, an L value of 1, an m sub L value of 2, and an m sub S value of 1/2. The reason, if n equals 2, which is the case here, you can have an L value as 1 or 0, because remember, L can be from 0 to n minus 1. So an n of 2 and an L of 1 is perfectly valid. However, if L is 1, then m sub L can only go from -1 to 0 to 1. In other words, from minus L to plus L, meaning m sub L cannot be 2 as it is in this example. Therefore, the set of quantum numbers with n equals 2, L equals 1, m sub L equals 2, and m sub S equals 1/2 is not valid. Finally, let's determine the set of quantum numbers for an electron in the 3p orbital. We want a value of n, L, m sub L, and m sub S that is valid. I'll give you a hint. There are 6 possible correct answers to this question. Pause the video, come up with your correct answer, and then hit play to see if you were right. If n equals 3, or if it's a 3p orbital, then n equals 3. If n equals 3, then L can be anything from 0, 1, or 2, but because it is a p orbital, L must be 1. If L must be 1, then m sub L, which can go from minus L to plus L, has to be either -1, 0, or 1. And because we are talking about an electron in the 3p orbital, m sub S can be either plus 1/2 or minus 1/2. This leads to 6 possible combinations of quantum numbers that could describe the electron in a 3p orbital. You will note that in the 3p orbitals, there are a maximum of 6 electrons possible. In practice, each one of these sets of quantum numbers describes one of those 6 electrons. Because we didn't specify any further than 3p, we would have to accept any of these 6 possible answers. We could narrow the possible answers by saying, for example, all electrons, this particular electron has to have a positive 1/2 spin, in which case only the 3 answers in the left column would be possible. We could also narrow the possible correct answers by specifying the value of m sub L we wish the particular orbital where the electron resides had. I hope these examples and this explanation have shed a little light on the meaning and importance of quantum numbers. In subsequent chapters, we will use these quantum numbers to write electron configurations for all of the electrons in various elements.